Hello, everyone, and welcome to the workshop on introducing the Tenstorrent Model Zoo by Milan Kordic. Milan is a senior machine learning engineer at Tenstorrent and a member of the customer success team. His role is to support Tenstorrent customers and the community of machine learning developers using Tenstorrent hardware to successfully build and deploy their AI solutions. With an educational background in electrical and computer engineering and past work experiences as a machine learning engineer, data scientist, and analytics engineer, Milan has a strong background and knowledge of AI and machine learning systems and computer hardware architecture. So without further delay, I hand over the session to Milan. Thank you.
Perfect. Thank you so much, Afshin. Just doing a mic check, everything. I guess everyone can hear me okay. Perfect. Okay, why don't we get started? So good afternoon, everyone, or kind of good morning, depending on where you're joining us from. Thank you for taking the time out of your busy schedule and joining me today for our workshop on introducing the Tenstorrent Model Zoo. My name is Milan, as you heard in my introduction, and to reiterate, I am a senior machine learning engineer on the customer success team here at Tenstorrent, based out of Toronto, Ontario, Canada, which is where I am right now. And I'm very excited to be here today sharing all the great work that Tenstorrent is doing to advance the capability of AI and machine learning. Now, today's workshop will be part presentation and part hands-on coding. And I will be coding using Tenstorrent software and hardware, which I am aware that many people currently at the moment do not have access to. But the concepts that I'll be presenting are transferable really to kind of any device or more in kind of the broader machine learning development cycle. I am coding using Python and going through the standard machine learning or deep learning workflow. And this is by design because part of Tenstorrent value add is that we want to keep our software simple and easy to use so that when you do get access to one of our hardware solutions, the switching cost of your software infrastructure remains low. So with that introduction, let's get started. I'll start by a little bit just presenting kind of a bit of a background on who Tenstorrent is. Since I realize a lot of people might not know, we are a startup company based here out of Toronto with offices kind of pretty much all over the world now. But essentially, Tenstorrent builds next generation computers. Our mission is to address the open source compute demands of software 2.0 through industry leading AI and ML accelerators. So those are the chips you see on the left there. Through high-performing RISC-V CPUs, and then infinitely configurable ML and CPU chiplets. And today, we're very proud to offer our line of AI and ML accelerators, which you'll see in a minute, but we're equally proud of and excited about all the work that we're doing with our RISC-V CPUs. And so you may be aware that there are a lot of efforts in the community going around on advancing AI and ML compute demands. And so your question might be asking yourself, well, what makes Tenstorrent unique? What is our advantage? And here's why we think that we win AI and ML. A few different contributions go into our strategy. One, and what you'll see today, is our easy to use software. That's something that's core to our mission and to our development. And some of the details that surround that is we're able to execute higher math per instruction simply because of the software stack and the hardware architecture design. We perform efficient tensor reshuffle, where we have the ability to run batch one and high efficiency and to be able to apply conditional computation. As well, given our design, we have optimized data movement and compute that is near memory. So all these are kind of leading to advantages. But on top of that, we also are focused on milliwatt to megawatt, what we call scalability. So being able to go from using a single chip for an application all the way scaling up to racks of devices and server-sized deployments. And diving a little bit into the hardware. So today, as I mentioned, my demo is actually running on Tenstorrent Silicon. And so this is just kind of a close-up, very high-level view of that device that I'm using. It's our Gray Skull. It's our kind of first-generation product, our AI accelerator. And this is what's currently available from us in the market. But we're not stopping there. We do have a continuing developing roadmap with our second-generation product in development, and then designs for future generation products that we're working for on the AI accelerator side, as well as the CPU cores that I mentioned earlier, and then the integrated chiplets that we're working on. So kind of the point of this slide is to dive a little bit just to get that bird's eye view of kind of what the chip looks like. And it's really made up of this array of these tensor cores that are doing all the deep learning model computations that I'll be running today. And now diving, so you heard a little bit on the hardware side, diving a little bit to our software stack, which makes us quite advantageous. So really, software has emerged as one of the hardest obstacles in cracking the ML training and inference market. Tenstorrent software stack, so I didn't mention this earlier, but we have the capability of running both training and inference on our devices from all the different popular machine learning frameworks and different machine learning architecture designs. So frameworks, we can run PyTorch code, TensorFlow code that's models that are coming from Onyx or TorchScript, and different types of model architecture. So we have the ability to run a lot of the natural language processing popular models like transformer-based BERT and GPT, T5, BART, and then all the computer vision models like ResNets and object detection models like YOLO and SSDs. And so this is kind of a higher level view of our software stack. So at the top there, starting with those ML frameworks that I mentioned, so PyTorch, TensorFlow, even JAX we're working on, we are able to take all those down, convert them to a graph computational net using a lower level compiler, TVM, and then our software stack then lowers that even further down to those 10.6 cores with very optimized placement of operations in order to be able to improve the efficiency and the computation of processing these models, both for training and for inference. And this is all fully automated framework, so you get high quality results really with no manual effort. And it's the same software stack that's on one chip or whether it's on many or thousands of chips. And just to continue the discussion a little bit further on that software side, so our high-level software, really what the highest framework is something we call the PyBUDA library or PyBUDA stack. And these are just some code snippets and some cheat sheets around how exactly that software stack works. But the idea is, this is our interface with the Tenstorrent hardware, and it's the machine learning framework that allows you to develop the applications you need in order to train and inference on Tenstorrent hardware. And like PyTorch, PyBUDA gives you the flexibility in defining your own model architectures. So not only can you port the existing model architectures you have, or even popular ones from frameworks such as Hugging Face, but you can also use the API to design your own layers and your own architecture with the core capabilities and functionalities that are programmed in. And so this is more of it's more of a flexible software stack we have. But then on top of that, we have, and what I'll be kind of presenting today is our higher level stack, which we call the Tenstorrent Model Zoo. And so it's basically built using another custom Python library we developed called T-Thunder. And the purpose of the Model Zoo is to really package some of the more common models into a user-friendly, quick-to-use API so that you can do your training, your evaluation, and your deployment in as few lines of code as possible, all running on the Tenstorrent hardware. So again, this is kind of a step up from the PyBUDA software. If you've already kind of configured and optimized your code in that layer, you can then abstract it away in this layer of what the Model Zoo uses. And then you have quick to use, easy models that you can drag and drop, pull down into your environment, and you can deploy this into whatever kind of solution that you have. And so kind of our broad vision, our idea here is that there will be a public Model Zoo that's available where you can download models and train them and run inference on Tenstorrent hardware and deploy it. But also we have constant development where we're always integrating newer models into the zoo. But there's also this optionality of having a private customer zoo which is just for your own it's your own closed environment where you can use the same level API to create your own models and deploy them in whatever kind of environment you want. And that's only kept to you or your organization or however you're working. But you still have access to all the really popular ones like the ResNet, GPT, BERT, etc. And that all runs on hardware. So that was a pretty brief introduction, very brief introduction into Tenstorrent hardware, software, what we're doing, kind of what we're up to at the moment. Now I'll switch a little bit more into what our demo here today will be about, what the workshop really is focused on. But to sort of preempt that discussion a little bit, I just want to kind of go over an overview of maybe somebody who's not very familiar with a typical deep learning or AI model workflow. Typically what happens is there's 4 stages to model development. Really, there's 2 high-level stages. One is training, one is inference. And then each one, both training and both inference, can sort of be split off into 2 subcategories. So start with the top left here under the training, under pre-train. Pre-train is typically what happens when you're starting off with a model that has never really been trained at all. You're starting with random initialized parameters, in this case, weights. So this is sort of a skeleton of what would be a very simplified deep learning model. And all your weights, really, they don't hold anything very valuable, because when you put in a sample through it, you're not really going to get anything meaningful out of it. So you run your forward pass with whatever, in this case, we're doing an image classification task. We put in a picture of an airplane, model's telling us it's a bus. It really doesn't know what it's doing, but we initialize this training process where we have our error, and we have our backprop step. And continually over many, many iterations, these weights start to get better at recognizing whatever it is you're putting into this. In this case, it's an image, but it could be a text. And you're feeding it a large sample of data. Now, this pre-train step is very computationally expensive. So in this demo, I won't really be running through that. We do have the capability to run it, but it's a very long time-consuming process. So models like BERT and GPT are trained on days and days of continual training, running computation to get that base, or what we call the pre-trained model. And these models are typically what constitutes sort of what are called foundational models. So again, the BERT, the GPT, the ResNet, they're trained on a very large corpus of data. And they're very good generally. They have this kind of good base operation. But what we want to do is usually for use cases, we want to take it a step further, and we want to run this fine-tuning process. So what's the difference between pre-train and fine-tune? Well, fine-tuning is you're still training, you're running the same operation, but now sort of you're running it for a few extra iterations on a smaller data set that's very specific to your target application. So in this case, we're doing image classification, but what we want to do is we want to do image classification for cats and dogs. So the only pictures we're feeding into this model are images of cats and dogs. And now our model is going to start to fine tune, or it's going to start to get really good at this one particular task using the same process. And the benefit of fine tuning is that usually you need a smaller data set than what you use for pre-training, and you need fewer steps or iterations. So it's much more computationally efficient and time consuming. In our workshop, we'll go through actually fine tuning a model. So you can see how that looks using the Model Zoo API. And then moving on, so once now you have a trained model, or what you think is a pretty good model, and you want to run an application, before you can actually kind of deploy that model, you generally want to evaluate it, or you want to test how good it's running. So we have this evaluation step here, where what you typically do is you feed it another data set, not the same data set that it was trained on, but what's called an evaluation data set, which is also just a smaller, varied data set. And the idea here is you don't actually do any backwards propagation training. You're only feeding it through, and you're evaluating what that output is, and you're comparing it to your ground truth label. And so you can generate some metric that says, your app model is this % accurate, or your F1 score is this, or really depends on the use case you're working on. You'll have different metrics. But here what you're trying to do is you're trying to get some of that, how well is my model performing? to come to that go, no-go decision of, okay, is this something we want to deploy, or do we need to go back into our process and maybe we need to collect more data, maybe we need to alter the model, et cetera. Could be many sort of operations. And I'll show exactly how we can run evaluation on a small subset of data using Model Zoo API. And then the final step, when you have a model, you've evaluated, you're very happy with the metrics, you think this is something that is going to give you some business value and you're able to put it into production, you can deploy that model to take in single or batched inputs, and you essentially run that prediction on data that it has never seen before, but it's got a pretty good performance, and it's giving you good results that you can now use in your downstream application. And through this workshop, we'll go through this process of actually, once we had a fine-tuned and evaluated model, we'll deploy it, we'll build a quick little API around it that we can use, and we'll see how that looks when it's deployed and running on Tenstorrent hardware as well. And so kind of showing this kind of parallel picture now, jumping forward, the 4 stages, but with TT Model Zoo, again, we can run all 4 of these steps in very few lines of code. So that's kind of what we're showing here, snippets of code using the Model Zoo API in order to pre-train a model, fine-tune a model, evaluate it, and then use it for running prediction. But I'll show how to use that API to actually then deploy it. The code is a little bit more involved depending on what kind of serving infrastructure you want to use. But you essentially can use it to actually do single instance prediction on data, on new raw data. And so let's go into this demo. So I'll start off just by kind of setting the stage a little bit of what we're going to be going through. So I mentioned earlier in those last couple of slides that we want to be fine-tuning, evaluating, and deploying. And we're going to be using a BERT-based question and answering model using the Squad v1.1 dataset. And to just give that a little bit more context to explain what's going on. So BERT model and Squad. So BERT, as I kind of mentioned, is once it's pre-trained, it's one of these foundational models. So it's the pre-training that happens with BERT is that it's really trained on 2 tasks. So one is called language modeling, where about 15% of the tokens that are in a sentence are masked away. And the model is trained to try to fill in those gaps or predict those words within that sentence. And then the other task it's trained on is called next sentence prediction. So it's trying to predict, if you give it 2 sentences, what's the probability that the next sentence will come after the first one. And so really what is happening behind the scenes here, why are we doing this task, is we're training this model to give it contextual embeddings for words and to give it some deeper understanding or sort of a general understanding of the language in itself. So kind of word associations, that underlining sort of understanding of what the words mean. Now, the BERT training, pre-training itself, we know is very computationally expensive. In fact, the original BERT model was trained on, the BERT-based model was trained on 4 cloud TPUs over 4 days, 4 continuous days. So it really can take a very long time to train this kind of base model. So, given our constraints today, we're not going to go through that pre-training process yet. And then once you have that kind of base foundational model, then you want to use that model for some other tasks where we kind of mentioned that fine-tuning. Now, there are different types of tasks and objectives you can do. The one we're going to go through is question and answering, and using the Squad dataset. So we're going to fine-tune for this particular task. And fine-tuning, again, it does depend on the task, the data, your metrics, but generally it could take you maybe up to 2 hours on a single GPU, typically is what's trained and fine-tuned. So something that's a little bit more manageable. We will fine-tune a model, but we're going to do it for not 2 hours. We're going to go maybe for just a couple minutes just to get a sense of how everything is working. But that is the process. It's a much shorter process for fine-tuning, and it's for a specific task. And so for us, our specific task is question answering. So a little bit of background, what are QA systems? QA systems is basically you give it some form of context, so a paragraph of some kind of text or information, and then you can ask questions about that text, and then the model will give you responses. So where is this useful? It's useful for things like fact checking, where you can ask a question, is this fact true or false? And it can query some text and it'll give you the answer. Customer service is a very useful application. So things like maybe chatbots you might see, where you can ask a question, automate, and you get an automated response where it'll query you wherever it's kind of looking from to get you that answer. That's kind of on technical support, used for market research, and it's also used for generating reports or conducting research. So lots of very good applications for question and answering. And then a little bit on the data set we're using. So this is a publicly available data set. It's called the Stanford Question Answering or SQUAD data set. And this is a data set that's put together, I believe, yeah, it's over 100,000 different question and answering pairs from 500 plus articles, and really kind of very hardly see it here, but what happens is you get this massive paragraph of text, and then you basically have these questions you asked and what the answer to that question was. So in this case, this text here is all about Super Bowl 50. There's a question that says, which NFL team represented the AFC at Super Bowl 50? And the answer is the Denver Broncos. And if you were to read this text, you would find that, yes, in fact, it's telling you that the Denver Broncos represented the AFC. So that's kind of what that model is doing from a fine-tuning perspective. And just let's go through very quickly what our workshop objectives are today. So everything here we're going to be doing with the Tenstorrent Model Zoo API and Python. And we're going to go really through 4 main tasks. We're going to fine-tune BERT based on SQUAD v1.1 dataset. We're going to evaluate this fine-tuned model to get kind of a sense of what performance is like. And then we're going to deploy this fine-tuned model on an endpoint for inference. And then we're going to create a quick, very demo dashboard to actually be able to query. And it's going to look something like this, where we can provide it a paragraph, some context, and we're going to be able to throw in a question in there, and it'll give us an answer to, based on what our context is, what it's going to answer our question for us. And one final slide, I promise this is the last one, some keynote for running the Model Zoo. What you'll see when I go through it is really there's 2 main components. There's the Model Zoo API, which we're going to see in a minute. And so for these 4 tasks, you have a little bit more involved. You'll see the code, but you have essentially these classes that were created that are wrappers around the code around that you need in order to run these models on the hardware. And then we need configuration files to basically kind of set the parameters, to point to where the data is coming from, what device we're running on, so on and so forth. And we'll go through some of the details on these. But these are really the 2 main components you need. So you need a configuration file to set your parameters, and you need your library or your API, and I'll show you how to set all that up so that you can actually run the model. So let me quickly jump over to the code itself. And right here, so we can see the screen up here. Okay, perfect. Okay, so I'll be kind of going through what you would see in a typical development environment. A lot of engineers, developers, we kind of typically use an IDE. So in this case, I'm using VS Code. And we'll go through actually developing the code that we need in order to run our model. So I have my terminal here. What I'll do is I'll first start off by actually creating a script file we want to do. I'm going to start off with actually creating a script file for evaluation, because what I want to do first is I want to evaluate the base model before doing any training, just to get a sense of kind of what are our starting parameters are, or what's our benchmark performance. And then I'll do some fine tune. We'll write this script where we're going to fine tune for a few iterations. We're going to evaluate on the fine tuned model, and we're going to see how much better did the model improve after fine tuning itself. So I'll start off here by creating a new script file. So this one we're actually going to do fine tuning first. So I'll just give it a name. I'll say BERT. We want to do SQUAD, and we want to do on Tenstorrent, and we want to evaluate. So that gives us a script, and I'll just give it kind of a quick comment header just so we know what we're doing. So we're doing BERT SQUAD. We want to do evaluation on TT grayscale. Okay, so a couple things we want to do. First, we need to import some of the relevant libraries and packages, kind of your standard approach. So one package we need, it's called Pyralis. So this one is really for parsing, it's for parsing command line code, but we can also use it with the API encode. Actually, what I'll also show you is right here, I'm writing it in script format. But all the commands I'm going to be doing here, we can also do it in a command line interface. So we have everything available as command line. I'll show you both approaches. This one's a little bit more in-depth involved, and I think it's a nicer way to highlight typical machine learning structure for a model. So we're going to use this. This is going to be to parse our configuration file. And then now we want to read in from our models API. So this is our Model Zoo. So you can see actually we have a list of different models that we can use. In our case, we want to go with BERT. And then the different tasks, what we can do with the BERT model. In this case, we want to build a script for evaluating. So we're going to import from BERT evaluation. We want to import the question and answering predictor. So this again is the wrapper that's going to be used to actually run prediction on a question and answering model. And we also need another API called evaluation loop. And we need a configuration class that we have that's custom designed for this model. So these are the three sort of classes, packages that we need. And now I'll just start with the standard if name equals main, because we're going to run this as a script from our terminal. And the first step now you want to do is, so let's say step 1, you want to load your configuration. Now we don't have a configuration file just yet, and that's okay. I'm gonna create one in a minute, but we can still create kind of that skeleton code to say, okay, well, I know I want to read one in using Paralis, and I'm going to parse. And what this API needs to understand what is the configuration class we're using. For us, that's config we pulled in. And then it needs to know the configuration path of that model. So in our case, I have kind of a directory already set up, but we're going to create this YAML file in a second that basically shows us what are all the configuration settings we need. So that's step 1, is to load your configuration. Step 2 is now you want to load, you want to instantiate an instance of that model. So it's the question and answering predictor. So we need to create and initialize that class. And it needs a couple of things. It needs to know, okay, from what configuration, and we'll see all the parameters we set. And it needs this variable called numClasses2. This is just sort of that it's basically taking 2 kind of inputs is what the model will take. And then what we want to do is we actually want to run load dataset, and I'll explain this in a minute. So load dataset is important because we're running an evaluation task. It needs to load in the evaluation data that you're going to use, right? So it's not going to be just a single kind of data sample. You're feeding it a larger set of data that it's going to run through the internal data loader that's built up, process, do all the pre-processing, and then it'll run through. And then you need to set one parameter we have, which is called our loop. And this is sort of telling it what does it need to loop through. And there's a few sort of parameters. We need a data configuration. So we're going to do config data, and we need eval examples where we take from our model as well after it's been loaded. And we have a couple other ones. So we have example indices. It's going to take from example indices and eval features. Okay, quite a bit going on there. But really what all this is doing, what step 2 doing is it's instantiating the model class. And I spelled that wrong, but that's okay. And now step 3 we can go to. So step 3, quite simple, it's run evaluation. And all we do for that is we say model.run. And now with this code, what will basically happen now, this is all the code we need to create that evaluation loop. So again, going through it again, step 1, load the configuration, and we'll create this file in a second. Step 2, instantiate the model class, load the configuration parameters, load the data, set its loop that it wants to run through. And then step 3 is actually run the model. And before we can run it though, we do need to create that configuration file. And so what I'll do here is we want to make sure it's the same name, what we put in the code. So squad v1 eval.yaml. And when we open that, now I'm going to cheat a little bit here because I already do have these parameters available, but I'll walk through what they exactly are so I'm not typing them all in one by one. But essentially, these are now the parameters of our model. So sort of higher class, we have some data parameters, we have some experiment parameters, and then a couple kind of model specific parameters. So some of the important ones I'll run through. Number of epochs, in this case, we just want to do one because we're evaluating. We just want to go one pass through the model. And experiment type, we're doing inference. So if you recall, evaluation and prediction falls under the inference category. So we want to run inference. I'm going to comment this one out for a second. What this one is doing is if you have a model, and this will become relevant when we fine tune, if you have your model checkpoint weights, you can load from that. I don't want to load from it in this case because I just want to evaluate the bare BERT base model on the dev data set. But later we'll include this parameter back in and we're going to see how it's going to change once we load in the fine-tuned weights. And then a couple of parameters, we want to specify what our batch sizes are, how many batches we want to go through, what each batch size is. We specify our data set path. So in this case, we're using squad v1 dev, and we have our evaluation script. All of this is stored, our data is formatted in JSON formats. This is something that's very important depending on how you set up your model. It does support different data formatting reading options. You just have to do a couple more different configurations within the API, but by default, it will read your data from a JSON file. So this is something that's stored on my local, and all the dev data is in here. And this one specific task to the model, actually two. One is I want to run everything on Grayscale hardware. So I did mention we do have other generations of hardware available. Right now, I'm just evaluating on Grayscale. And for BERT config, I'm using BERT Tiny here. So BERT has different sizes available. So there's BERT Tiny, BERT Base, BERT Large, BERT Small. The difference between all these variations of BERT is simply the size of the model. So the tiny one is the smallest one. Basically what that means is it has less parameters. Trade-off there is it's going to be much faster to run, but it comes with a loss of performance compared to something like BERT base. So the reason I chose tiny here was just because it's going to be faster in this sort of 20-minute, 30-minute demo. But if you had a couple extra minutes or an hour or two, you could definitely do like a BERT large model and it'll just perform much better, really. And so that's all we need. So now we have our configuration set up. We have our evaluation script. Now all we need to do, so moment of truth, is actually run this script. So we're going to run BERT squad eval, BERT squad TT eval, and we're running this just on the and let's see what we're wrong there. Okay. Squad eval.py. Okay, let's try this. Okay, so we're going to run it using this. I'm having some issues with Python here. We're running it using the command line interface. And I probably typed something wrong. Oh, you know what? There we go. Now it's running. So it's reading from the checkpoint. Didn't leave the configuration parameter there set. Let's see. Checkpoint. Okay. But anyways, what it's doing there is actually it's reading from a checkpoint file. So we're going to see when it evaluates it. I guess what it needs is a base checkpoint file to be able to run and evaluate. So right now, it's doing that. So what you're seeing happening on the screen now is first, the code is all compile based. So it has to first compile. But once it's compiled, what you can do is you actually store that as an image file so that you only have to go through this process one time, only really the first time you write the model. But once compiled, then you can read it as many times as you want. You don't have to wait for this long process. And then what's happening here is you saw it go through all the evaluation iterations. So it went through 647 steps, like we defined, and it's just now finishing up, and you'll see the results pop up in a minute. And there we go. And so on this particular model, actually, it's probably better if I just open the results themselves. BERT question and answering is really evaluated on two metrics. One of them is called exact match. This is a percentage that tells you from your data set how many samples that it predict spot on. And you can see, again, this model didn't train for very long. It's kind of the base model. It has a very low score. And then your F1 score is kind of traditional. Your F1 in this case is 14. So obviously the model is not performing very well, but you can see the process it went through to generate that evaluation. And now similarly, what we can do, so I can clear all this, is, you know what happened? That didn't save. There we go. Okay. That's why I didn't run. Okay. Well, what we'll do now is we'll jump and we'll do the fine-tuning script so we can actually train a model ourselves. And to do that, what I'll do is I'll just create a new file, and I'll call it BERT squad Tenstorrent fine-tune. And you'll see actually how very similar in process this is to what we just ran. So let's give it just a very quick title to keep things a little bit neat here. BERT squad, we want to do fine tune using TT Grayskull. And very similarly, we want to import our parsing API. So this is to actually read in the configuration file. And now we can read in from our Model Zoo API. So again, we want to use BERT, but this time we want to fine tune a model. And from this library, what we need to import is we need to import our TT BERT for question and answering. So again, this is a custom class that was created specifically for doing question and answering on BERT to take in any sort of type of data. And there are other classes available for tasks like named entity recognition or for other kind of base models that are coming. But we're using BERT and we're doing question and answering. And we also need a loop class here. So this is the fine tune loop. And we need our configuration class. And so now very similarly, we want to run, we kind of want to just set up our typical Python kind of running. If this is main, then run this file. And going through the very same steps. So step one that we saw before, we want to load config. And so for this, we just want to say configuration equals, we want to use the Pyralis. We want to parse our input file, which is coming from config class is going to be config. And then our config path is going to be configs. And again, we haven't created this config file. We're going to do it, but it's coming from squad v1 and finetune.yaml. So we'll see in a minute, we'll create that configuration file and how is the fine tuning configuration different than evaluation. But step two is now same thing, instantiate the model. So we're going to say model. In this case, we're using TT BERT for question and answering. We want to set the configuration to be config, what we just loaded. And we're using two classes because we're feeding it two inputs into the model. This one, we actually don't need to preload anything. Our loop is going to do that for us because it's a training task. It just it's preset to actually, so data config, we're going to use config.data. It's actually preset to do it. And then finally, step three, we want to run. So we just say model.run. Okay. Now let's give this guy a shot. So we're going to save this. And now when we call Python, BERT, squad TT, fine tune, .py, this one giving me the same error. Nope, okay, perfect. So, oh, and it did. So it doesn't, yes, so we didn't create a configuration file. So let's do that. So we're going to do squad v1. This is good. This is live debugging and programming in real life. So fine tune YAML. And I'm going to cheat here a little bit again because I've already created this file itself. But I'll explain the key differences for this one. A couple things, same thing. We have our sort of batches. We're going to do batch size 32, and we're going to do a total of 128. Reason I'm doing 120, actually, I'm going to even drop this to make it even faster. This is basically saying how long you want to train for this and our number of epochs. I'm going to keep this to 32 and 1 because I want it to go by really quickly. Again, you could set this, the longer you set it for, the longer it's going to train and the better performance of a model you're going to get. But for demonstration purposes, we're going to do very short run. Similar thing, I need to feed it the data. So it's coming from training data. It needs to know what device to run on, in this case, Grayskull. Data sequential is just how it's feeding the data in. So this is a parameter that we have to set to true. And then we have a few other tags here, but the main one too is we're going to be using BERT tiny to train our model. But once all that's saved, now we can give this another shot. BERT fine tune. And what's going to happen is it will have to, so it's loading the data. Now the data is being cached, so there is some pre-processing steps that I kind of ran before to save time. So it is loading the cache data. But what this is doing is it's actually recompiling the model again because it's training a new model from start. Now I should also mention all this verbosity you're seeing here is this can all be controlled and turned off. I left it on because it's sort of the developer mode and it's kind of cool to see everything going on behind the scenes. But in sort of a real life setting, this can be, there's a parameter that can turn all of this verbosity off. So what you only really care about is once you run and you care about getting that flag at the end that tells you everything is done training. So it takes just a couple seconds to actually get everything compiled and it's going to start the training loop. But in the meantime, what I can do, what we'll see here is under results, you can actually see already, here's today's date, it created that file where it's going to store the weights. You can see here, it's already running through and it's doing its training iterations. And when it's done, similarly to this one, like I trained before, it's going to create a new checkpoint file, which it's done now. And so now we get a new checkpoint file, and this is the model that we just trained. And so if we wanted to go back and evaluate this model, what we can do is just in our evaluation config, what we need to do is we need to just change this. So we're going to use actually today's date. So let's copy relative path. Let's put it in here. So now what we want to do is we want to evaluate the model we just trained. Again, I don't expect it to perform very well because we trained it for very, very little samples and epochs. But what we can do is we can do Python BERT, and we want to do eval.py. When we run that, it's going to basically go through, and now it's going to read this checkpoint, what we just did, and it's going to run evaluation on that model itself. And so you can see here, it's loading the weights. Takes a second or two to run all through the data, compile, run through the data. But what we'll see in a second is the results of that model. Yeah, so the one thing is, yeah, every time you do train a new model, you get new weights, it has to sort of recompile itself. But once you do it once, you can save it, and then you don't have to go through that process again. So here it's running through all the evaluation data, and it'll give us a metric at the very end. And here it's done. And let's see how our model performed. And there we go. So not bad, actually. I'll pull up the result. So that got overwritten. And you can see now, exact match is very low. It's less than, it's 0.1%. Kind of no surprise. We did it from base, and then the F1 score is about 6. So again, no surprise. It didn't really train for long. The model I ran evaluation on earlier was one I sort of had as backup that I trained for many longer iterations. So that's why you saw a bit slighter improvement. So that covers what we wanted to do for running model evaluation and fine tuning. But now really we want to use this model, right? The whole point of going through this process was that we want to train a model on our data because at some point we want to deploy it and we want to build a product or service or something around this model, or whether it's internal or external, but make this model useful. And so what we want to do, and I've already kind of gone ahead and kind of pre-wrote that script, but what we can have is this script file here that I'm using Fast API for, where I'm actually going to use the question and answering handler from the BERT. In this case, I'm using BERT inference, and I'm going to deploy a handler. And the configuration file for this is I'm reading that checkpoint file itself. So what it's going to do, it's going to load up the configuration as we saw before. So there's this initialization step. We're going to load the configuration file. We're going to instantiate the model. We're going to do a few extra steps that we want to do. Really what these steps are doing is they're compiling that model ahead of time. And so that when it gets hosted, all it does is it's ready to take in a new request. And so that it doesn't have to recompile every time. So this is kind of very straightforward boilerplate Fast API code that you can use to really deploy any type of model. In our case, we're using, again, the Model Zoo API because this is what's linked to the Tenstorrent hardware. And so really to run this, all we need to do is there another package, it's called UVcorn. But what I'm doing here is basically I'm setting the host. So this is the workstation I'm using that has Grayscale hardware, and I'm telling it to run this BERT TT inference app. And when I do that, fingers crossed, all going well, what we should see is that it should start up the process, create the server, and it's actually going to host it. And here it read in the checkpoint files. While we wait for that, I'm also going to go through this process of showing you, here, showing the actual app then that we're going to deploy. So what this is going to do is this is just going to deploy to an endpoint. And really what that means is that that endpoint now can take in requests and it'll give you some results. But kind of a little bit boring. Oh, so you can see it now, it's running on this one. And it's a little bit boring because you don't really get some kind of cool flash sheets, API around it. You don't get to see any kind of design. So what we can do is we can actually create a little app around it. And that's the code that you're seeing here. What I have is I use Streamlit in this case to create just a little front end here that really what it's going to do is it's going to issue a post request to that address. So you can see here, this is where I'm hosting it with my predictions, QA English model, a little bit of design. And then here, what it's going to do is it's going to take some input and it's going to give us an answer. So in order for me to run this, all I really need to do is just say Streamlit run, and we're going to call it app.py. And this usually just takes a couple of seconds to spin up. And there we go. And so what it did here was it actually opened for me. So here's our Tenstorrent little app we just created there. And now what we can do, apologies for that. What we can do is we can query it. So let me just pull up something we want to query with. I'll move this over. So we want to maybe, I already have some sort of samples we can use. But let's say, so one of my favorite inventors is Nikola Tesla. Let's say we enter a paragraph here, some information about kind of Nikola Tesla taken off of Wikipedia, a brief little introduction. And now we want to query it and we can say, all right, well, when was Nikola Tesla born? And here we get a response that says 1856. And kind of show you where all that was running behind the scenes. So this is all done on the Grayscale hardware. And when I pull up our kind of command here, you could see that at that point, when I ran the command, it gave it as an input. The device made its prediction and it gave us a result. And now here it's waiting for another sample. So what we could do is we can even do, any other examples as well. But I'm looking at time here, and that's kind of a very quick high-level overview of what we had. I want to leave maybe 10 minutes or so for any questions and answers. But yeah, hope you enjoyed that demo. Hope it was kind of clear, and happy to take any questions. Right, I can go through the list down here and see if there's any. Oh, Safa's question. Okay. How did you fine tune? Oh, okay, yeah. So fine tuning, let me just quickly pull up the code again. This one. There's our, okay. Fine tuning is quite straightforward. So, I mean, everything that's actually going on behind the scenes is abstracted away in these two classes. So in this TT BERT for question answering and question answering fine tune loop. So you don't really get to see the details that are going on, because in your case, all you're really concerned about is setting the specific configurations you need, like where's your data coming from, what type of model, etc. But what's happening behind the scenes is it's using the PyBUDA software. And again, it's very kind of similar design to PyTorch, wherein what it's doing is it's going to create your model, and it's going to have a forward function, and it's going to have that training loop where what it's going to do is it's going to run a forward pass, compute the error, run your backward, run your optimizer, and then that's going to continually loop and then update your weights, run optimizer, update the weights, and that's continually looping. So that's what this loop actually is doing. So question answering fine tune loop, it's doing that process behind the scenes. You just don't see it because it's all been kind of abstracted away. And so to change what it has to do to recompile is really if you change any sort of the parameters, any of your architecture, it will recompile in that instance. So the reason it's recompiling here is I didn't save an image anywhere to load from, but that was a step I could have taken to kind of save some time, is have that image available and load from there. Yeah, hope that answers your question, Safa. It's training, exactly. Yeah, fine tuning is just it's just training. The only difference is really the only difference between doing training here is the fine tune API. It's a very specific model for a specific task, right? So kind of looking back at the slides, fine tuning, what we do, if we wanted to pre-train, we could pre-train, but we would be pre-training a base model, something like BERT or GPT. But the fact that we're fine tuning is typically it's for a very specific task. So what we want to do is we want to fine tune BERT for question and answering, right? We could also have, there's API that says fine tune TT BERT for NER. So if we wanted to do name entity recognition instead of question answering, we could train a model for that. We could also do TT BERT for sentiment analysis, where basically you give it a sentence that says, you know, that movie is awesome. And then the model will say positive, negative, neutral. So fine tuning really depends on the task you want to do, but they're all building on top of that base model in this instance. Medred, so what would be the benefit of using Model Zoo individual natively? Would there be need to create custom for Grayskull as new AI? The benefit of the Model Zoo really is that for some of these kind of Model Zoo is that as models become online, so when you look at the development, we're always constantly grabbing new models, optimizing them for the hardware, and we're bringing them to public Model Zoo so you don't have to go through those steps. Everything's already been optimized for you for that particular model. And so if you're doing a task that just sort of requires one of these base models, then the benefit of Model Zoo is you don't have to go through that optimization step yourself. Now, if you are interested in doing that, if you're maybe coming more from a research background where you actually want to dive into the layers of the model and experiment with different functions and that, then I would say Model Zoo would not be your first step. You would want to go and revert. You could actually do it in PyTorch, or you can do it using Tenstorrent software called PyBUDA, where it gives you that flexibility to go into those details. And then I would say once you've done that experimentation, optimization you want, and let's say you have a final product you're happy with, then you could always bring it to the Model Zoo for future cases if you want to just kind of quickly iterate on that. But yeah, I would say if you want to have more granularity and how deep you want to go into the model, Model Zoo is not going to be your first stop. You want to kind of deal with that other high-level packages instead. Yeah, I hope that answers your question, Medrad. Oh, perfect. Cool. Can we have the repo link? So not yet. So the repo currently is still not publicly available. Our intent is to open source at some point. It's just we're still kind of in some development phases. We're still doing some optimization and fine tuning. But eventually, all this code, all the repos will be publicly available. And as kind of more of the hardware gets out there, it will be available for people to use. So this is just more of a demo of the hardware, but also typical machine learning workflow. Oh, sorry, Medrad. Second question, would we need to create custom packages for Grayskull as new come to the scene? So for Grayskull, we are always kind of upgrading that software stack itself with new packages that are relevant. At the moment, it's all kind of done internally, but once it gets to that open source point, then it will really be open to anybody to kind of integrate what kind of tools they want using this sort of API for running hardware, right? So really, we're just one component of the larger MLOps ecosystem in that we do the compute and we try to simplify that training and deployment process on our hardware as much as possible. But for things, if you're looking at, data management systems or different sort of, in my case here, we use Fast API for serving. But if you wanted to use a different serving tool like Flask or TorchServe, really all that should still be available to you to use. But you just have to kind of like integrate this underlying model training code into that. Cool, awesome, yeah. Okay, we've got a couple minutes left. If there's any other kind of questions, happy to answer them. If not, feel free also to connect with me on LinkedIn. You can find me just under my name, Milan Kordic on LinkedIn, or if you go under the Tenstorrent webpage, you'll find me there. Other than that, feel free to email me. Email is mkordic@tenstorrent.com. Happy to answer any more questions or go through more detail if there's anything else you would like to see. But yes, yeah. Eric's points there, right? So Model Zoo is already optimized. Optimally, yeah, exactly. Cool. Thanks, Sergey. All right, thank you. If there's nothing else, then thank you everybody for joining us today. Hope you had something out of value for this. And again, feel free to connect and stay in touch.